Good afternoon and welcome to the ESAB Specialty Alloys live event. My name is Clemente Tallarico and with me as the presenter we have Mr. Peter Stones and Mr. Per-Åke Björnstedt as well for technical support. I'm pleased to announce here the fourth presentations of ESAB Specialty Alloys, which will happen every third Friday of the month at 14:30 European time via Team Live event. The fourth presentation of the program will be the one starting in a few seconds with the title What You Need to Know About Nickel-Based Filler Metals. We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box you will find on the top right of your screen. We intend to present on about 30 minutes and take 10 to 15 minutes more for answering your questions. So, and now let us start with the show with Peter presenting. Enjoy.
Thank you, Clemente. Good afternoon, everyone. It's my pleasure to be here doing this presentation. As Clemente said, it's the fourth in the series. A couple of things I'd like to mention is we intend to take about 30 minutes to deliver the presentation, and we'll take about 10 minutes after that for any questions that are posted in the Q&A boxes. Please don't worry about taking notes or if I've not covered anything in sufficient detail. We're more than happy to supply copies of the slides if you just drop us an email, and both mine and Clemente's contact details will be given at the end of the presentation. So, as I said, this is intended to last for around about 30 minutes, so it's a bit of a taster of the topic, and we hope that it's of sufficient interest. And as we say, should you want any more information, please don't hesitate to get in touch with us afterwards. So the objectives, what I want to try and get across in the 30 minutes is why we use these nickel-based alloys. What are the properties that we use them for? I think we're all familiar with the corrosion resistance properties. What I want to do is describe basically how they work. So what are the mechanisms and what influences the properties that these nickel alloys have? What influences the properties? What do we use these properties to best advantage for? Which applications? So I want to talk about some applications. There's a little bit on the history of the development of the grades. Yeah, you may know that some of the commercially available alloys are fairly recent inventions. Obviously, we're a welding company, so we'll talk about the welding processes that are available and give a quick, brief summary on some guidelines on how you weld nickel-based alloys. And then I'll just illustrate the portfolio, what's available on the market now. So, the super alloys, nickel-based alloys, they were created for use in gas turbines. That was the requirement at the time. The metallurgy and the materials around at the time were really not good enough for the applications that were being invented at the time. So the development is really only in the last 70 years, and it's been driven by requirement of the parameters that the equipment's being used in. So higher temperatures or lower temperatures. One of the key factors about the nickel alloys is that they have a good stability for temperatures up to 85% at the melting points. So why are these things so expensive? Well, we say they're nickel alloys, but they can contain anything up to 10 other elements in them. And the typical elements that are in there are things that are on the list. Chromium, molybdenum, but some more exotic elements like boron, hafnium, rhenium. So what do they do? What properties do they imbibe in the nickel-based alloys? So forgive me for going back to the textbooks really, but to understand the microstructure of the nickel-based alloys, you need to appreciate that it's the matrix, it's the the form, the matrix, the form of the material in the nickel alloys due to the composition, the way it's made, due to temperatures. So the basic matrix of a nickel alloy is this face-centered cubic austenitic, or gamma, called a gamma matrix. So that's the background of everything in a nickel alloy. And then what gives the strength are these also face-centered cubic, but they're intermetallic precipitates. So gamma prime, it's called. So it's nickel with either aluminium, titanium. What these do, they're precipitated in the matrix, in the gamma matrix, and they're dispersed in it, and they lock the grain boundaries. So by virtue of the composition, by virtue of the temperature, then we get these intermetallic precipitates dispersed. So they're precipitated, they grow inside the matrix of nickel, the gamma matrix of nickel. And the result of that is that they drive pegs in there, if you like, and stop things moving. And that gives them an enormous strength. Okay. In addition to that, we've got these carbides, borides, and other phases like delta, gamma double prime, various other phases and carbides. And again, these are distributed through the grain boundaries and the matrix. So again, you've got all these elements as a result of the composition pinning everything together. As these matrices lock into place, then that's what gives the nickel alloys their strength. That's what gives them the properties. It's a nice schematic of the evolution of the microstructure in a nickel-based alloy. Obviously, we've got the grey area everywhere. Is the gamma, is the nickel gamma matrix. Then you can see the gamma prime starting to form in nodules. As they lose some energy, they start to align. Okay, so you can see it's like almost like a street block. Okay, and then we've got carbides being dispersed at the grain boundaries. So that's kind of a schematic of what it looks like. Why? What's the reason for adding all of these expensive other elements into the alloys? And again, I don't want to read the list out completely, but this is what the key effects are. So you can increase the mechanical strength by putting tantalum, rhenium, cobalt in there. Promote the formation of the gamma prime. If you're promoting that formation, then you're going to lock everything together. Okay, so I don't want that to happen quicker, slower, whatever, and it varies in the various grades of nickel alloys that are available. Corrosion resistance, of course, and then increasing the ductility. Okay, so it's necessary for some elements, maybe not for filamels, but certainly for some constructional nickel alloys. Applications. So what are the properties that we utilize, the properties of the nickel-based fillers? What are they that we utilize, why we pay so much money and use these nickel alloys for the special applications? So obviously corrosion resistant properties, resistance to pitting corrosion, intergranular corrosion, stress corrosion, cracking, high temperature corrosion and scaling. Low temperature, cryogenic application. So the mechanisms that lock everything together at high temperature, again, they still work at low temperatures. Okay, that's why we use nickel alloys for very severe cryogenic applications. And then high temperature again, strength and creep resistance. They're the main reasons why we use the nickel alloys. And in which segments of business do we use? And petrochemicals. Obviously, petrochemicals covers a wide range of chemicals and some of the most corrosive environments you could possibly think of. All kinds of acids, all kinds of alkalis, and just about everything else in between. Upstream, downstream, oil and gas. Again, so whether it's on the surface or subsea, the requirements, the amount that it costs to put a manifold on the bottom of the North Sea is 18, 20 million, you need to know that it's going to last a few years. The nuclear industry is an obvious one. Waste incineration to power generation is becoming more and more popular. A lot of countries are insisting on these kind of plants being built. And so the requirements there, you've got a bit of everything. The corrosion resistance in burning household waste, it can be huge. And then an obvious one is LNG, liquid natural gas. Cryogenic application, so either for storage or transportation. One of the biggest users that there are on the planet for nickel-based alloys. So, utilising corrosion resistant properties, just want to touch briefly on the most common types of corrosion and why the nickel alloys are so good at resisting this, basically. So, pitting corrosion is a result of the passive surface. So all stainless steels, nickels have nickel oxide or chromium oxide surface that's passive. It's got a micron thick layer on there, and it will keep corrosion out. If that gets damaged for any reason, and particularly in a chlorine environment, then it starts a reaction inside. There's no oxygen in there, and so you get an oxidation, and it's like an iceberg. So there's a little pit on the surface, but underneath, that's where all the damage is. And it's quite a nasty type of corrosion because it's not measurable, it's not manageable. Okay. Crevice corrosion, it works in the same mechanism as pitting corrosion, but it's mainly by design. So for an overlapping weld, you have a crevice in there. So the surface of the metal could be damaged, and there's a crevice not allowing any air in there, for example. And so you get the same effect, and it starts to eat away. This example that we can see on the right hand side is a tube in a tube sheet on a heat exchanger. So the end of the tube's been damaged by virtue of it being pressed into the tube sheet, but there's no other treatment. So if you welded it, then there wouldn't be a crevice. However, there is a crevice, so you see this type of corrosion. Intergranular corrosion. This is something that happens at grain boundaries, whereby at certain temperatures, you get carbide, chromium carbides precipitating at the grain boundaries. And these are these blacker lines that you can see there. So the schematic over here, you have chromium carbides at the grain boundaries, which basically means it's leached the chrome from the grains. So the chrome in these regions could be very low, and you don't have a stainless, you don't have a corrosion resistant alloy anymore in those areas. The solution for that is good high purity filler metals. Low carbon or stabilized grades with niobium, for example, they're very much less susceptible to this type of precipitation. And it can all be put right with a post-weld heat treatment. We wouldn't normally recommend doing a post-weld heat treatment, but in some cases it has to be. Stress corrosion cracking is something to be aware of, particularly in austenitic steels. But you need a combination of the material being under a strain in a corrosive environment and at temperature. If you've got those three things happening and you're using an austenitic stainless steel, then it's a problem, and one or two of them need to be designed out somehow. The good news is for the nickel-based alloys that it doesn't occur. This type of corrosion does not occur in nickel-based alloys. In terms of the volume of filler metal used, nickel-based filler metal, the largest in the world is for weld overlay. So overlay cladding of pipes, manifolds, boiler tubes. Here, for example, that's the external cladding of a boiler tube. Here's the internal cladding of a large manifold, and not to forget strip cladding. Strip cladding, again, we cover strip cladding and particularly electroslag welding. Strip cladding is a separate topic. but strip cladding, you're able to achieve deposition rates anything up to 90 kilograms per hour, whereas typically for a wire TIG, you maybe get up to 9. So the difference is huge. The most common welding processes are everything that you would expect, really. MIG, TIG, hot wire TIG in particular seems to be being used a lot more on wire overlay. So the high temperature properties, this next section is a little bit dull in that it's a series of graphs basically illustrating the properties of alloy 625 or nickel chrome moly 3. And really, there's no better way to illustrate the good properties and the reason why this particular grade is used at high temperature. So for this, it's showing that you've got a high tensile strength at a high temperature. There you go. For the second one, it's essentially the same. It's tensile up to a temperature of 650, then it starts to decrease. Fatigue strength, again, 80 degrees, 800 degrees Fahrenheit, 427 degrees centigrade, you've still got good stress figures. Okay, creep strength, if you're going to high temperature, then we talk about creep rates per hour, per 1,000 hours, I should say. And you've still got relatively low creep rates at a high stress, at a high temperature. I think this is the last one, scaling resistance. So this is a periodic cycling of 15 minutes of heating, then 5 minutes of cooling. And you can see the amount of weight change per milligrams per square centimetre over 800, 900, 1,000 hours is virtually zero. So all of these properties, all of these graphs are just illustrating that the 625, the 625 is the one where most of the data is available. That's why we use it. The high temperature applications that these things are used for, furnace muffle tubes is a fairly popular one. Heat exchanger tubes, gas flares. Obviously the temperatures at the end of the gas flares are huge. We've seen externally clad boiler walls before, and again, gas turbine components. Low temperature. Whenever you talk about low temperatures, and particularly stainless steels and carbon steels for that matter, sorry, you have to talk about the ductile to brittle transition temperature. So this is it's a phenomena that, and the graph illustrates it very, very well. If you're starting at a high temperature, then the fracture energy is very high. You've got a ductile material. It's as ductile as it is at room temperature, for instance. As you start to reduce the temperature, then there's a transformation, and different metals are affected in different ways. But there's a definite transformation whereby you've gone from ductile to brittle. So if you're not careful, if you've not designed correctly, then at this level, if your weld is operating at this temperature, then there's a possibility that you're going to suffer a brittle fracture. Okay, and again, we should know about this. All ferrous metals exhibit a transition. However, nickel-based alloys don't. So again, it's something else that you don't have to worry about. But again, that's one of the properties, one of the phenomena why the nickel-based alloys are used in cryogenics. For low temperature applications, storage tanks, the graph is showing that basically down to -88 for ethane, -88 degrees centigrade for storage of ethane, then the type of material used in the tank is anything up to 3.5% nickel, and you can weld it with the same alloy. However, you go below that, so at around the -100 degrees centigrade mark, then you have to increase the amount of nickel in the base material. So this would be the base material that you make the tanks from. As you get even further down, over -200 or below -200, then 12% nickel steel is the type of material that you'd need to use. And the difference with these is that the 5% and upwards of nickel steel, they need to be welded with high alloy filler metals. And generally, the 12% nickel is welded with a nickel-based alloy. So, as I've mentioned, the main use, the main used alloys for LNG tanks are alloy 625 and alloy C276. So, nickel chrome moly 3, nickel chrome moly 4. Nickel chrome moly 4 has been around the longest, so there's lots of outstanding WPSs, for example, in the design specifications. It was the material of choice for some time, and it tends to have been overtaken lately by nickel chrome moly 3 or alloy 625 for superior mechanical properties, essentially. So to talk about the most common filler metals that are available, we'll just spend a couple of minutes going into the history. Obviously, the gas turbines were in use in the war, and then the development of the nickel alloys really started after that. So they came out with this, the first nickel chrome moly alloy was this alloy C, which was around in the 50s. And then the problem with that was that it couldn't be welded. So alloy 625 was invented, nickel chrome moly 3. It was the first nickel chrome moly alloy that could be welded. And that was really done by the addition of niobium. Okay. It took a few years after that when nickel chrome moly 4 was produced, alloy C276. So the development was that it had low carbon and silicon, so it could be welded without the use of niobium. So it was another way of producing a weldable material. A little bit later, we had this alloy called C4, and they had the bright idea to put tungsten into it to basically eliminate sensitization. So it made it less susceptible to sensitization. C4 is really not so common these days. 1980, so it's in fairly recent history. 1980, it's certainly since I've been alive. Alloy C22. So it's got a higher chrome content than C276 and the C4 that were produced prior to that. It's got a higher thermal stability, okay. However, a lower corrosion resistance in reducing media. Alloy 59. Again, it's only in the 1990s that alloy 59, nickel chrome moly 13, became available commercially. So it improved on the corrosion resistance in chlorine, and it's niobium free. It's a pure ternary nickel chrome moly alloy, so it's got the highest local corrosion resistance and thermal stability. Pure ternary, it's a description of, if you looked at the phase diagram for this alloy, it looks an awful lot cleaner than some of the other ones because it's got less in it, in a nutshell. Alloy 686 is the highest alloyed of all the chrome nickel moly alloys, so it's got the best corrosion resistance in most applications. It's the highest alloy, it's generally one of the most expensive, as you'd expect. However, it is thermally unstable above 1200 degrees, so obviously you've got to be very careful welding that. In terms of what is commercially available, the Exciton range, we have 9 grades there, all listed in various ways. The way that we name them is by the nickel content. So Ni41Cu is our 825, Ni60, 60% nickel is our 625, for example. In addition to that, ESAB also have a range, some of which overlap and some of which are unique. But suffice to say that we do have these available as solid wires, stick electrodes, and we do have submerged arc wires and fluxes. So quite extensive range is available in either the Exciton or the ESAB range. In terms of welding solutions, the nickel alloys are superaustenitics, and the problem with a superaustenitic is that they are all austenitic. There's no ferrite in there, and a microsection of them illustrates the size of the grains. The grains are always very, very big with very few grain boundaries. If there's no grain boundaries, there's nothing. This material just wants to crack. If you heat it up and cool it down, it just wants to crack. So you have to be very careful to avoid centerline crackings when welding these materials. You can make a very good looking weld, but as it starts to cool down, you get this type of effect, a centerline crack. And again, because it's a superaustenitic with no ferrite in it, it's very vulnerable to impurities. So any impurities that have come from the base metal, from dirt, for example, or it may be even in the filler metal itself. Any impurities such as phosphorus and sulfur, they're the most common ones. What ferrite will do is basically absorb that and make it non-effective. It doesn't have any properties. If there's no ferrite in there to absorb it, then what happens is that the phosphorus and sulfur will change the melting point of parts of the metal. So as it's cooling down, it doesn't have the strength to hold the sides together. There's not enough material in there, there's not enough strength in there to hold the thing together. So to compensate for that, there's a few things that we can do. I would always say always use filler metal, so don't try and weld nickel alloys autogenously. Keep the heat out as much as possible, so no preheat, no post-weld heat treatment. As I said, the only post-weld heat treatment that we would recommend is a full solution anneal to get things back, if you have to. Typical max heat input is 1 kilojoule. Put some material in the weld. Don't try a convex weld bead. Try and put some material in there to give it a chance of holding everything together. Critically is a good fit up to keep the residual stresses low. If this thing's under strain, there just won't be enough strength in the weld to hold it together, and it will crack. In terms of your technique, use stringer beads. No weaving. Weaving increases the heat input. It's much better to use multiple passes of small diameter wires rather than one big pass of a large diameter wire. Use stringer beads. Avoid dwell and backfill your craters. So if there is a crater, then fill it up. You need the material in there to hold it together. Before you even start welding, then the design and preparation of the joint is essential. The more highly alloyed the filler metal, the less that it wants to flow, and the more like chewing gum it becomes. So you have to give the welder a bit of a chance and make these root gaps wider. If you don't give him the chance, then there's a more than a good chance that you'll get lacquer fusion. He won't be able to run the weld pool into the bottom of the root gap. I've mentioned before the welding process, the most common. All the usual typical welding processes are available, right up to submerged arc and strip cladding.